look at now is these trigonometric functions, and it's related again to this circular motion, this angular motion, so it's all related to each other. And I want to talk about how the sine wave is created, and then the tangent and the cosine. The most start off. Obviously, if we go through it, why that's the most important one. We want to bear in mind what we already know about angles. So this thing is rotating around here. At time 0, we assume it starts here, at 0, and then rotates anti-clockwise as time goes by. So after a certain amount of time, it's reached this point. With an angular velocity omega, and after this time t, it's moved to an angle theta. So the first thing we can do is say that actually we have already got the relationship between the angular velocity and the angle. The angular velocity is the angle divided by the time. So rearranging this formula, we've got that theta equals the angular velocity times time, which fits in. What angle does this thing move? It's the rate at which it's moving, the angular velocity, multiplied by the time. So as time goes by, it's rotating. At any given moment, what's the angle theta? Omega times t. So whenever we've got theta, we could replace that with omega t. Now, as this thing rotates around, after time it's reached here, we're often interested in how far this thing has moved in a certain sense. So at time 0, how far has it moved in the y plane, in this y-axis? At time 0, it's not moved at all in the y plane, so it starts at 0. But as it comes around here, after time t, we could say it's moved this distance up the y-axis. A little bit later, and it's moved to here, it will have moved that distance up the y-axis. Again, assuming that initially we're going to consider unit vector, so it's length, radius of 1, this radius of rotation. At this point, it's moved a distance of 1 up the y-axis. So as far as angles is concerned, it's starting at 0, and after we've moved through 90 degrees, we get to 1. So if I were to measure this angle, I'd say, right, at 0, how far has it moved up the y-axis? It's not moved up the y-axis. After 90 degrees, or what is that in radians?
Pi over 4.
Nope.
2.
Pi over 2, yeah. So we're going to always have this in terms of radians now, because angular velocity is to do with radian measure. We can say that it's actually reached a height of 1. So that would be 1 on this axis. Now we consider the rotation carrying on. Go back to our rotation model. So here we are. We continue to let this thing rotate, and we can see now that actually the distance along the y-axis is coming back down again until we get to 180 degrees, or pi radians, back to 0 again. So after pi radians, we're back to 0. We continue to rotate. But now as we come round here, yeah, we're going negative now, so we're going negative on the y-axis until we get to, what would this angle be? Measured from here, this angle, not quite. That's half a pi, that's pi, this is 1.5 or 3 pi over 2. Yeah. So at 3 pi over 2, we're at negative 1. 3 pi over 2, or 1.5 pi, we're down to negative 1. So if I say negative 1 is about here, then we'll be about there on our sketch. And then we go back full circle. So we're coming around this part now, rather, and we get back to 0 again. So 360 degrees or 2 pi, we're back to 0. And we have a plot of all the angles. So if I were to now say, fill in these here, what this wave is that I've produced, and the sine wave, I think you recognize it, is in fact a plot of all the positions along the y-axis as this thing rotates. So after 45 degrees, what's 45 degrees in terms of radians? Pi over 4. On your calculator, please, work out what the sine of pi over 4 is. So you need to be in radians on the calculator. So you check you're in radians and then work it out. So the calculator will tell us how far up the y-axis this rotation has gone. That's what it's telling us effectively. How far have we moved up the y-axis at that angle? So at 45 degrees, we've gone 0.7071 up the y-axis, assuming, and this is a big assumption, that this is 1. Okay? So that if I typed into the calculator sine of pi over 2, I'd get 1. The sine of pi over 2 is 1. However, if we look at this, of course, it gives us more angles than that. If I look across from here, I find that actually this angle is also 0.7071. What angle is this?
That is
If that's pi over 4, this is pi over 2, what's this?
pi over 2 pi.
It could be
2 pi over 3.
3/4 of pi, or 3 pi over 4, won't it? Yeah? What's that in degrees? If that's 90, that's 45, that's 90, what's this?
135.
135, right. So if you type in the sine of 3 pi over 4, you should get the same answer. 0.7071. Now also, of course, if we come across, then the positives, we could carry on, and if you think about it, if the cycle continues, I've also got this angle, which is a whole turn, which is 2 pi, plus another quarter. So 2 1/4 pi, 2 quarters, that's 9 over 4 pi, will also give 0.701, and so on. So there's a whole infinite number, if you think about it, of angles that have a sine of 0.7071. The calculator just gives me the angles in between 0 and 90 degrees, effectively. And then we've got to work out the rest ourselves. Liam's point about the negative, because of this symmetry between this part of it and this part of it, if I go to this point, which is pi, halfway between pi and 1.5 pi, which is 1 1/4 pi, so that's 5 pi over 4. What's the sine of 5 pi over 4? It should be negative 0.7071. Try it. So with our knowledge of the sine wave and the calculator, we can find how far up or down the y-axis we've travelled in this rotation. Here it is rotating around here for any angle in terms of radians. It might be positive and it might be negative. Okay? Now, this axis is time, so what we're doing is we're actually saying we can work out the displacement in this vertical direction as time goes by. And that's useful because this could be a voltage produced by a generator, or it could be some sort of rotating force. We can find out the magnitude of the force in the y plane for any time, because we can work out, eventually we've got a formula that we can use to calculate it. Y, the value of y, is going to be the sine of theta. We've just worked that out, but theta is omega t, so therefore y equals sine omega t. Sine function. If I know the angular velocity, I multiply that by the time it's been rotating for, That will give me the angle, making sure I'm in radians, and then the sine of that angle will give me the distance I've moved up the y-axis, which is often what I'm interested in. Okay.